today on how it's made. Oil pressure sensors. Large format printing. Heavy equipment simulators. And head and neck restraints. In motor vehicles, an oil pressure sensor is a critical part of the engine. As oil lubricates, cools, and cleans the motor, this sensor constantly measures the pressure and signals a problem before it causes serious damage to the engine. Screwed to the engine block and connected to the car's computer, the sensor can detect the smallest change in oil pressure. The computer relays the information to the gauge on the dashboard. It allows the driver to tell at a glance if there's a pressure problem under the hood. To manufacture motor oil sensors, a robot picks up a perforated ceramic board and transfers it to a carriage. The carriage shuttles the board into a screen printing machine. It squeegees palladium silver paste onto it, creating a pattern for a sensor around each of the holes. The silver will serve as an electrical conductor. A trip through a long oven bakes the silver paste onto the ceramic. Then it's back to the screen printing machine. This time, the squeegee applies a green glass glaze onto the silver. The pattern leaves some of the silver exposed for the attachment of components like capacitors and diodes. A robot then applies those components faster than you can blink an eye. The next robot transfers terminals to the sensors. To align the prongs of the terminal with exposed silver on the sensor, the robot takes a picture and sends it to the computer. The computer then guides the positioning. It all happens in a flash. Once the terminal has been soldered to the sensor, another robot dispenses adhesive around the components. This seals the circuitry from the oil that will flow through the center hole. The next robot places a silicon chip on the sensor, covering and sealing the center hole. This chip will react to changes in oil pressure. Another robot bonds the silicon chip to the circuitry using aluminum wire that's thinner than a human hair. This completes the electrical connection. An employee now inserts the ends of the sensors in a fixture and breaks them along score lines. This separates them into strips of 5. She transfers the strip to a machine that bends the terminals to a precise shape. She snaps the ceramic along more score lines to separate the strips of 5 into single sensors. Next, she connects the terminals to posts and plastic housing. After soldering them in place, she folds the rest of the sensor over them. She then places brass shells in a carrier. She inserts 2 rubber O-rings in the shells, a large one and a smaller one around the center hole. The robots take it from here. The first one picks up the sensor assembly and, using a camera as a guide, transfers it to the brass shell. Then it's over to a press and crimp station. The top tool applies pressure to compress the O-rings, as forming tools crimp the shell around the sensor. An applicator coats the threads of the brass shell with sealant. When dry, this sealant will enhance the sensor's fit to the engine to prevent oil leakage. A test head probes each sensor, performing a full electrical evaluation. It also applies air pressure to test for leaks. After passing the test, the oil sensor is complete. Businesses looking to advertise will often commission a printing company to produce a large poster or banner. The quality of large format printing is better than ever, thanks to digital technology. Commercial equipment can typically print a banner up to 16 feet high by 150 feet wide. If the required size is larger, it's printed in sections, then joined together. A pre-press technician preps the client's design for printing, adjusting colors, sectioning, and adding a bleed. This is a blank border around the design because the machines can't print all the way to the edge. Then it's time to load a roll-to-roll printing machine with weather-resistant vinyl mesh. They feed the leading edge of the roll into the machine and pull it through the output end. This aligns the vinyl so that the printing won't come out crooked. They slip a cardboard tube over the roller, which will receive the printed vinyl and tape on the leading edge. If this job required printing on a rigid material, they'd be using a flatbed printer rather than the roll-to-roll. Both machines print with inkjet technology, similar to a home computer printer. However, rather than using dye-based inks, they're typically solvent-based. They're designed to withstand outdoor conditions for 3 to 5 years. The machine uses the standard inkjet colors: black, yellow, cyan, and magenta. It also includes light cyan and light magenta to provide additional shade variations. The machine has 12 print heads, 2 per color. Each head has 256 nozzles. Once daily, they're put through a full cleaning procedure to prevent clogging. The print head moves back and forth across the vinyl. The computer guides the individual nozzles to deposit dots of ink at specific spots. All those colored dots together form the printed design. The first 6 inches the machine prints are a color bar test to make sure that every nozzle is working properly. The printing of the actual design follows. The printed vinyl banner exits the machine and winds around the receiving roller. Then they mount the roll onto another machine, which trims off the excess vinyl and the bleed with rotary blades. When the banner is comprised of sections, workers connect them. First they align the edges, then they bind the joint temporarily with masking tape. They flick a switch to project laser lines, which indicate the width and center of the weld. The weld will permanently connect the sections on the reverse side. Turning the banner face down, workers align the joint with the center line. A magnetic strip secures the banner to the table to prevent it from shifting, and a vacuum pulls the banner taut. At the same time, a hot air welder fuses the joint with heat-activated adhesive tape. Then they flip the banner face up again and remove the temporary tape. The last step is to reinforce the perimeter with webbing, the material used for seatbelts. This gives the banner a nice finished edge. It also creates a strong border in which to secure grommets for hanging the banner. Workers apply the grommets manually with a pneumatic press. A banner typically has a grommet every 24 inches, plus 3 in each corner. To hang the banner, you run bungee cords through the grommets, pull taut, then hook the ends to plates affixed to the building facade. A few screws for reinforcement, and you're done. Wind passes right through the tiny holes of the vinyl mesh, so the banner doesn't billow. When you're learning how to operate heavy equipment, one wrong move can cause damage or injuries. That's why it's becoming more common to train on a simulator, which can replicate real-life scenarios, from typical maneuvers to emergency situations. Whether learning to operate a crane, backhoe, or excavator, it's safer for a trainee to make rookie mistakes at a virtual worksite. The instructor simply installs heavy equipment controls and loads the appropriate software. Then, the simulator is all set to replicate how the equipment maneuvers. A heavy equipment simulator begins life as a series of 3D technical drawings. Mechanical engineering technicians plug in the details of the customer's order, including foot pedals and joysticks, to control the equipment's various movements. Then assembly can begin. Following the plans, technicians build the steel motion platform, which replicates the movement of the cab. Its base has wheels for rolling the simulator from one location to another. This drive controls the 3 actuators which raise, lower, and tilt the platform. Once the technicians have installed and wired up all 3 actuators, they install the platform cover. Next, they mount the height-adjustable seat. At its base, enclosed in a bellow, is a pneumatic suspension system. This enables the seat to realistically bounce or jerk in response to the action being simulated. Meanwhile, another technician assembles the simulator's control box. He mounts the joystick controller and connects its wiring to a cable inside. The cable leads to a connector on the base of the box. That connector simply plugs into the motion platform right next to the operator seat. The box attaches securely with large screw knobs, making it easy to disconnect and switch to different kinds of simulations. The foot pedals are mounted to a separate platform. Technicians attach it to the motion platform with 2 screws. Like the control box, the idea is to be able to switch this pedal platform easily for a different one. The simulator's cab is now fully assembled, and it moves just like a real one. The virtual view from the cab spans 5 LCD screens to give the trainee a realistic perspective of the worksite. After installing the screen supports, workers mount the screens. The configuration mimics the window layout of the typical cab. The simulator runs on software that's designed in-house. However, the client can further customize the program for a specific make and model of heavy equipment, or to simulate specific scenarios that might arise on a particular worksite. The simulator has 5 different computers. 3 of them run the seat movement, the screens, and a small touchscreen to the trainee's right. That screen displays the buttons, knobs, and levers of the heavy equipment's dashboard. The 4th computer calculates the physics of the simulated environment, such as the excavator's digging movement and the corresponding soil movement. The 5th computer manages the training scenarios. For instance, an instructor can program adverse weather conditions to make the exercise more difficult. To simulate a different piece of equipment, the instructor simply switches the joystick and pedals if necessary, and loads the appropriate software. In the simulator, the trainee has the same perspective he or she would have in the real-life cab. 3 reflective markers on the helmet enable an infrared camera mounted above the screens to track the trainee's head movements. This prompts the software to display the corresponding view. Tragedy on the racetrack led to the development of the head and neck restraint in the 1980s. Investigations had revealed a deadly trend in motorsports. With the driver's body restrained, the head moved violently in a crash, causing fracture to the base of the skull. Clearly, more restraint was needed. Attached to a helmet, a head and neck restraint is designed to save the racer's skull. It has become required equipment in many racing organizations. To make these restraints, they mix plastic and carbon fiber pellets. The carbon fiber fortifies the plastic, which is made of castor bean oil instead of petroleum products. A machine melts the mixture and injects it into a mold under pressure to produce the base structure for the restraint. The operator breaks off what's known as the sprue, plastic that's solidified in the channels leading to the mold. He trims the plastic and carbon fiber overflow from around the edges. This overflow is known in the industry as flash. He hangs the parts to cure over a 24-hour period. The next day, the employee clamps the part in a jig and activates computerized tools. The first one drills holes for tethering the restraint to the helmet. Another trims it to its final size. An automated hot knife now cuts nylon tether material to the correct length. Then it's over to a computerized sewing machine to stitch the tether around a chrome fitting. The stitching pattern has been designed by an engineer to withstand the force of impact. The operator then stitches on a label, which says the tether's design has been sanctioned by both American and European racing organizations. Next, using a die powered by bursts of air, A worker punches out shoulder pads from cushiony foam. The next member of the team slides the shoulder pads into casings made of fire-resistant cotton. It's a snug fit, and without a special installation tool, the job wouldn't go smoothly. By folding the pad into the tool and then inserting it into the long case, there are no bunch-ups. Some head and neck restraints are adjustable, so drivers can find a more comfortable fit. They assemble those restraints in 3 pieces with the adjustable fittings in the joints. The employee then paints adhesive primer onto the base structure of the head and neck restraint. He coats most of the plastic and carbon fiber surface with it. He applies neoprene padding to the prime surface. The padding is adhesive backed and it bonds instantly. He attaches the tether to the back of the restraint with plastic clips and screws. Using hook and loop tape, he secures the shoulder pads to the underside of the restraint's yoke. Another worker applies more certification labels. They signify that the actual structure of the head and neck restraint meets standards. They now test a randomly selected restraint. A hydraulic arm pulls the tethers until the restraint snaps, mimicking the force of a violent impact. The restraint withstands more than what's required and breaks in the right place. Next, an employee attaches a head and neck restraint to the helmet using the tethers. 2 crash dummies put the restraints to the test. The one on the left isn't wearing a restraint, while the right one is. Steady nerves and a steady head could save a racer's life, and a head and neck restraint definitely improves the odds. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.